Okay, hello. So today we are having a lecture devoted to statistical meaning of entropy. Let's see if I have any chalk here. And at first I would like to start with the reminding a few things which we have studied during the previous lecture. During the previous lecture, I have introduced the concept of partition function. And I have said that for any system for which we know an energy spectrum, we can determine any thermodynamic value using this partition function. And I have used this, for example, I have determined an internal energy which can be considered as an average energy in a certain volume, which can be presented as sum of EI, where Pi is a probability for a system to have to be found in an energy level with an energy EI. And then this can be expanded as 1 over Z multiplied by E minus beta EI multiplied by EI. And then I have said that this sum can be presented as follows. And since I have a derivative here and we have minus in the exponent, we should add a minus here to compensate for this minus. And this means that this again can be written as and then we notice that this value inside the brackets is again a partition function. So I can find an internal energy as follows, as a simple derivative of the partition function. And I have said that actually you can determine any kind of a thermodynamic function using the partition function. Today we are going to study the entropy and how we determine the entropy. Thermodynamically we know that entropy can be related to increments of internal energy. So we know that du can be written as TdS minus PdV. So for these functions. So from this, at a constant volume, so assuming a constant volume, which is typically assumed when we study the statistical physics. Then dV is 0, and this equation becomes a bit simpler. du equals to TdS, from which we find that ds is du over t, or in other words, using this parameter beta, we can write that ds is actually equal to kb multiplied by beta multiplied by du. And from this we can find the derivative of this ds over d beta as follows. Okay, now finally finally we have this expression for the internal energy. So after we insert this expression into this one, we get minus Kb multiplied by beta multiplied by derivative over beta, and here we have reciprocal z multiplied by derivative of z over beta. So this can be treated as a definition of entropy, but this definition has a certain drawback. This is a differential definition. That means that using this definition we can find entropy only up to some constant. So we can, if we have some function s0 which satisfies this equation, then if you introduce another function s1 which is s0 plus a certain constant c, then this function s1 will also satisfy this equation. So that's a difficulty. That means that entropy is defined, is not a completely defined value, but there are certain principles which allow you to choose one of the quantities over other quantities. And this statement, which allows you to choose this constant in a certain way, is called third law of thermodynamics. According to the third law of thermodynamics, the constant in this expression is chosen in such a way that entropy at zero temperature, to make an entropy at zero temperature equal to 0. The quantity entropy, which is defined in this way, has more than simple thermodynamic meaning. It also has a very clear statistical meaning. Let's assume, we can show that the following expression for the entropy satisfies this equation. I am not going to show it now because it's quite complicated in terms of derivations and transformations, but nevertheless it can be shown that this quantity defined in this way, where Pi is a probability defined as this, then this quantity indeed satisfies this equation. But more than that, this quantity doesn't ring any bell, so it's quite complicated. We have some logarithms, we have some probabilities, and actually we don't know the final answer, so what this means actually. But well, just for now, I will say that this entropy is called von Neumann entropy. So actually, this quantity can be determined in terms of quantum mechanics, in terms of classical mechanics, and in quantum mechanics we can also have these probabilities introduced, and the final result that this quantity is a von Neumann entropy. And in order to find out the mean of this entropy, let's assume that we only have a single energy level, E, and this energy can be realized using n, so large number n, of different microscopic states. So this means that this energy level is degenerate. So we have a degenerate energy level, which can be, for which we can have n different states which have the same energy. So this is an example. This is an example. Of course, practical systems are quite different from this, but let's start with this very simplified example that we have only a single energy level, which can be realized using large number of different ways. So then, for this energy level, we can always write that Pi is actually always 1 over n. Because according to this definition, since we have the same EI for any state of the system, that means that all of the probabilities are equal to each other. And from that, using normalization condition, we immediately find that each of these probabilities is 1 over n, and then we can simply calculate this quantity. Okay, for this quantity, I also add Kb as a dimension constant. So we have entropy as Kb multiplied by sum over I, 1 over n multiplied by a natural log of 1 over n. Okay, it seems that I would also need to add a minus sign here. Okay, and then I have n terms. Each of these terms equals 1 over n multiplied by natural log of 1 over n. And that means that altogether, this expression equals to Kb natural log of n. So you can see that actually entropy is a quantity which quantifies the number of different realizations of the same state. So if you have n possible ways to realize certain macroscopic state, then the entropy will be proportional to the logarithm of this number of possible realization of this state. In statistics, this number n is typically called statistical weight. Statistical weight of the system. Okay, so we now have here statistical weight, and this expression here, where we multiply Kb by natural log of statistical weight, is called Boltzmann entropy. As you see, for this system, Boltzmann entropy is the same as von Neumann entropy. So that means that we are dealing with the same quantity. It's just different expressions for this quantity named after different people. But what happens if you study a more complicated, more realistic system which has a certain energy spectrum, which doesn't contain only one single level of energy? Then I would say that for this system, the probability density for energy looks like this. And as I have said on one of the first lectures devoted to statistical physics, devoted to molecular physics, when you have an energy of a system which is found as sum of different energies for different molecules in the system, when you accumulate a large number of random quantities, then the distribution for the resultant, for the sum of these quantities, becomes a very narrow function. And this is it. This very narrow function. So we can say that mostly the system occupies energy levels which are located very close to the average energy E average, or as we have noticed previously, this average energy is typically called internal energy. So that means that probability density function is centered around the internal energy, and mostly those energy levels which contribute to this expression of entropy are very close to this internal energy. And we have, and we know that actually the width of this function, delta E, is typically proportional to inverse square root of the number of molecules. So when we have a very large number of molecules, that means that the width of this function becomes very small. And for this reason, we can also apply this Boltzmann definition for entropy. So that means that for many cases, for many different systems, Boltzmann definition is a very simple kind and a meaningful and physically meaningful expression which allows you to understand the meaning of entropy. Of course, when we are dealing with the levels which have different probability of occupation, we need to use this expression, but well, this one gives you an understanding on what happens. And let's analyze this third law of thermodynamics using this concept, the concept of statistical weight. So the meaning is the following, that if the entropy at temperature, at zero temperature is zero, that means that for this certain system, a statistical weight that corresponds to the system, n, is equal to 1, because only a natural log of 1 will give you 0, as demanded by the third law of thermodynamics. And there is a simple explanation for this fact, that when you cool down the system to the temperature approaching 0, then if you have different levels in the system, there is a certain energy level which has the lowest energy. And this energy level is called typically ground level. Ground level. And for this ground level, we only have one ground state, which has this energy. Well, actually, in quantum mechanics, people are very interested in search of particular physical or quantum systems which may have degenerate energy level at the ground energy, and sometimes this system can be found, but that means that for these particular systems, for this very limited number of systems, we can say that entropy at zero temperature is equal to k log, well, I write here natural log of g, where g is a degeneracy of the ground level, so there are certain systems which violate third law of thermodynamics in this explicit form, but nevertheless, even if we have this type of system, we can write down that entropy at zero temperature is some finite number. And this is the most important part of the third law of thermodynamics. Okay, not energy, entropy at T equal to 0 is a finite number. So for the most physical systems, you can just use third law of thermodynamics in that form. But for a very limited, very special number of really rare and extraordinary systems which have a degeneracy at the ground level, you can write that entropy at 0 temperature is a finite number. And it's very important. This statement has very important consequences. First of all, let's remember an entropy, an expression for the entropy of an ideal gas. So sometimes it's written as as a function of temperature and volume. Entropy of the ideal gas can be written as this. And actually, well, there is a certain ambiguity when you find out natural log of dimensioned quantities like temperature and volume. But when you study increments of entropy, everything becomes very clearly defined. So we have CV multiplied by natural log of T final over T initial plus R multiplied by natural log of final volume over initial volume. So always the increments of entropy are very clearly defined. But what happens when we go to the limit of temperature approaching 0 in this expression? When temperature approaches 0, the log T, as you know, would approach minus infinity. And that's a problem. That means that we know for sure that when we take temperature approaching 0, then entropy goes to minus infinity, according to this expression. But according to the third law of thermodynamics, entropy, when temperature approaches 0, entropy should be a finite quantity. That means that this expression becomes invalid when the temperature of gas is cooled down to a very low levels. So when you approach 0 temperature, something happens with the ideal gas so that this expression is no longer valid. So this is not valid at T approaching 0. So let's look closer how we can satisfy this condition that the entropy should be a finite value when you approach 0 temperature. So let's study this quantity which is called CV. CV is a molar heat capacity at constant volume. So when you fix the volume of gas, and if you want to change the gas temperature, you need to supply an amount of heat delta Q, which is equal to CV multiplied by dt, to 1 mole of gas. Well, according to the definition of entropy, ds should be equal as delta Q over T. So this is CV over T multiplied by dt. So the most, I guess, the origin for this expression, for the main reason why this expression is not valid when temperature approaches 0 is that we have assumed that CV is some constant. But if we assume that, okay, we can write that TdS is equal to CV dt, and that means that when temperature goes to 0, then CV, which is found as T multiplied by ds over dt, should go to 0 too. Because we have temperature here which goes to 0, and ds over dt is some finite quantity. Because we have assumed that S is finite everywhere. And that means that when we change temperature here, to some finite changes of temperature correspond finite changes of entropy, leading to the fact that CV approaches 0. So third law of thermodynamics imposes some restrictions on thermodynamic variables. So if you assume that third law of thermodynamics is just a statement which allows you to choose some constant in entropy, which is not physically meaningful, then this example would show you that actually a third law of thermodynamics has lots of meaning in it. So if you have finite entropy, that means that you have some restrictions for thermodynamic quantities when you go to temperatures around 0. Next, I would like to discuss what happens when we mix two gases. So let's consider another example. Let's say we have a vessel number 1 and a vessel number 2. And this vessel number 1 is occupied by N1 molecules which have mass of M1. And vessel number 2 is occupied by N2 molecules occupied by gas number 2, and each molecule of this gas has mass which is equal to M2. Let's see what happens when we open a hole in the side wall of these vessels and allow for these two gases to mix with each other. And let's assume for simplicity that pressure and temperature for both of these gases are the same, so that when we open this valve, then when we open it, no change in pressure and temperature happens. So we can say that actually the change of entropy for these two gases is approximately equal to, okay, we have V1 volume and V2 volume here. So we can write that this is equal to the change in entropy for the first gas and for the second gas. So that gives us R log of V1 plus V2 over V1 plus R log V1 plus V2 over V2. Or we can write that this is R natural log of V1 plus V2 squared divided by V1, V2. And this expression is valid when masses of these molecules are different. M1 is not equal to M2. But what happens when this M1 is equal to M2? And in fact, when we open this valve, some exchange between molecules in the first and the second volume happens, but nevertheless, microscopic states remain the same. So when M1 equals to M2, actually, we can say that in total, this system consists of some gas which occupies volume V1 plus V2. And it happened before we opened the valve and after we opened the valve. So altogether, there is no change in entropy. It's very interesting that actually these molecules of gas can belong to the same chemical substance, like oxygen or nitrogen, but they can actually have different molecular mass. So as you know, there are different isotopes of chemical elements. So if you have different isotopes here of the same chemical element, and when we open this valve here, then entropy increases. But if you have the same composition of isotopes to the left and to the right, then there is no change in entropy. So this actually this is not a paradox, but this actually shows that entropy is a very tricky quantity. So when there is some change here, we have a finite change in entropy. But when there is no, then there is no change in entropy. So this is called Gibbs Paradox. And it was discovered when people have studied the concept of entropy, and it showed that if you assume, let's say assume that we want to study function delta S as a function of the mass of a molecule in the vessel number 2. So it says that this quantity is something R log V1 plus V2 squared over V1 V2 everywhere except for M1 equals to M2. Then the change in entropy is 0. And then when we change the mass of the molecule only very slightly in the second vessel, and again we have finite change in entropy. So the behavior of entropy as a function of M2, well, it looks like too unphysical. Mostly in physics we deal with functions and with quantities which have very smooth functional dependence. But here we don't have any kind of a smooth dependence. Okay, let's have a short break for 5 minutes. Okay, for the second part of the lecture, let's consider some implications, well, not implications, but some kind of consequences of the quantity of entropy and its meaning in many different fields of our life. First of all, let's start with this expression. This expression can be calculated not only for thermodynamic systems, but for other systems. For example, for text. So let's say we have a certain text. See, entropy is a quantity, so a certain English text. As you know, when this text is stored in your computer, it is being encoded. So each character of this text is encoded at a certain combination of zeros and ones, which is called bits, and we have 8 bits typically for a single character of an English text. So we have 8 bits, so 8 digits, which have one of two possible values, 0 or 1. And then we can study probability distribution for these combinations of 8 bits. So we can assume that the probability for a capital E to appear is let's say 1%. Probability of small e to appear in the text is some other quantity. And we can collect all of these probabilities from your text and then calculate the entropy of the text based on this quantity. But typically, in information theory, this quantity is slightly modified, and typically people calculate something like this. So they have probabilities, but the logarithm is taken, the base of the logarithm is not a natural exponent, but number 2. It's just due to the fact that we use a binary representation of data. That means that this quantity is more meaningful than this one with this respect. And it can be found out that for a simple English text, the entropy, as long as this text is long enough to be considered a thermodynamic system, the entropy of the text is about from 3 to 5 bits per character. So not 8, but 3 to 5, because we have letters and we have constrictions imposed that we use only certain combinations of ones and zeros here, and moreover, more than that, we also the probability of each of the character of English text to appear in this text depends on this character. Some characters appear more often than others, and it also makes a contribution to this entropy. But let's say we want to make some kind of an encrypted text, so we want to transfer a certain information to a certain person, but in such a way that no other person will understand what happened. And we need to encrypt this text. And we can encrypt it in different ways. So we can encrypt it using some kind of a ladder algorithm. So we can write like follows. So let's say we have this entropy is, and then with this rail fence algorithm, the encrypted text will read as EOSNREITY. Something which looks like gibberish, impossible to understand, but the main part, that this algorithm for encryption is not very safe, because the entropy of the result text is again 3 to 5 bits per character. And we can determine which kind of encryption algorithm was used. And when the algorithm is simple change of positions of letters or something similar, then the entropy of the text will not increase too much. And these types of cryptography algorithms are considered quite outdated. And for the modern cryptography, if we use modern cryptography algorithms, the entropy of the resulting bit sequence would be around 7.5 to 8 bits per character. Also, entropy has relations to the problem of archiving. So we want to compress, so if we want to compress some information in a, to let it occupy less of the space on your disk, then you need also to make some kind of encryption, or make kind of some encryption protocol, which is very simple to decrypt, because you want information to be compressed very quickly and decompressed very quickly. But the result is that you want to, for the entropy of this text to increase up to these values. So actually, when the entropy is small, that means that mostly these bits are redundant. So you can decrease the number of bits, so you can compress this text by increasing this entropy. So the maximum entropy of any bit sequence which is randomly composed out of zeros and ones, so the limit for this entropy is 8 bits per character. So when you encounter something, some kind of information which has less of an entropy, that means that this information can be compressed using a certain compression algorithm. But when the information has been compressed already, that means that there is not too much of a possibility to compress it further. So it's actually, you can say that the existence of a over-efficient or super archiver or super compression algorithm is impossible due to the second law of thermodynamics, because we have limits in entropy in the text. And when we have reached this limit of entropy, then we can continue no further. So modern data storage data storage algorithms are also devised to store videos and images. And also, for these storage algorithms, they are designed in such a way that the entropy of the resulting file should be almost equal to 8 bits per character. Otherwise, this image can be compressed further. And that means that typically images and videos take lots of space on your hard drives, and that means that when you improve a compression algorithm, and when you improve the speed of this compression algorithm and compression quality, then you would have a better storage, and you would have better capabilities for storing and processing video and image information. So that means that thermodynamics is not only related to completely thermodynamical systems like ideal gas or non-ideal gas, gaseous interaction. Many systems in our everyday life are obeying thermodynamic laws. Next, let's discuss a problem of negative temperatures. So first of all, let's start with some definition of temperature, which can be, well, related to probabilities. We know that the internal energy obeys the following formula: du is TdS minus PdV. And as we usually do in statistical physics, we assume volume constant. That gives you the temperature is equal to du over ds. Well, mostly it is done in an opposite way. A reciprocal temperature is determined as a derivative of entropy over the internal energy at constant volume. And actually, there is no reason why this quantity cannot take negative values. So let's say if we have a certain system in which entropy depends like follows as a function of energy, then here we would have positive derivative here and positive temperature, but here this derivative will become negative and the temperature will be negative too. Let's find an example for such a system which has an entropy dependence which looks like this. One of these systems is an ensemble of two-level atoms. So let's assume that we have atoms which can be found either in a ground state or in an excited state. And no further energy levels exist. So only these two energy levels. So here we can assume that the probability for a ground state to be occupied is equal to Pg. The same probability for the excited state is equal to Pe. And based only on these probabilities, we can calculate both the internal energy and the entropy. So for the internal energy, we have, this is Pg multiplied by 0. We assume that the ground level has an energy of 0, and excited state has an energy of delta E. So that means that the internal energy is equal to the probability for the excited state to be occupied multiplied by the energy difference between the excited and the ground state. And that means that this function can take values, so internal energy is a limited function which can take energies in the interval from 0 up to delta E. So the upper limit of energy when all of the molecules are in an excited state. Now for the entropy. Again, we use the definition for the entropy. So this is a P ground multiplied by natural log of P ground. Okay, here I forgot minus. And typically here we add Boltzmann constant in thermodynamics in order to preserve this equation. So here we have minus Kb multiplied by Pi multiplied by natural log of Pi. Here we also have minus here. Let me see where I have also forgotten minus. I think nowhere else. So minus PG log PG minus PE log PE. And we know that due to the normalization condition, PG can be found as 1 minus PE. So we can find actually, from the internal energy, we can find PE, and then we can calculate PG, and then we can insert them into this function and find entropy as a function of energy. And from this, we can easily calculate a temperature. So in these two-level systems, we find that PE is U over delta E, then PG is delta E minus U over delta E, and then entropy is minus, okay, here 1 minus PG, natural log of delta E minus U over delta E minus PG natural log of U over delta E. Okay, not exactly. So 1 minus PE and here PE. Okay, so this is minus So this is an entropy as a function of internal energy. So now let's calculate temperature, reciprocal temperature as ds over du. Here we have 1 over delta E multiplied by natural log of delta E minus U over delta E. Minus delta E minus U over delta E multiplied by derivative of this logarithm, which is delta E over delta E minus U multiplied by derivative of the expression inside the logarithm. And this is minus 1 over delta E. And this gives me 1. And minus by minus gives me plus. And for the second part, we have minus 1 over delta E natural log U over delta E and minus U over delta E multiplied by delta E over U multiplied by 1 over delta E. Okay, let's look further for this add this expression, and it gives me the following. So 1 over T is here 1 over delta E (1) plus natural log delta E minus U over delta E minus okay, minus 1 minus natural log of u over delta E. Okay, these two are eliminated from this expression. And finally, we have 1 over delta E, natural log of delta E minus u over u. So that means that when u is less than delta E over 2, then 1 over t is positive. When u is equal to delta E over 2, then 1 over t is 0, and that means the temperature is infinite. And when u is greater than delta E over 2, then 1 over t is negative, which means the temperature is negative. It's less than 0. So we can say that actually, if we look at the dependence of temperature as a function of internal energy, U, and here we have delta E over 2, here we have delta E. So what we have here, so when U is approximately is close to 0, then when U is close to 0, then here we have delta E, then here we have 0, which means that this quantity is infinite. And when 1 over t is infinite, that means that temperature is 0. Okay. And then temperature rises until it becomes infinite when we get close to delta E over 2. Then we immediately go, after here, we immediately go to minus infinite temperature. And then the temperature gets back to 0 from the negative side when we approach U, which equals to delta E. So formally, that means that temperature can easily be negative. Actually, instead of this derivation, I could do a very simple thing. In order to find the temperature, I could do something very, very simple and get the same result. As we know, according to Gibbs distribution, EI is proportional to exponent to minus EI over kBT. Minus EI over kBT. So that means that we can calculate the ratio of probabilities for the excited state to be occupied to the probability of ground state to be occupied, and it should be equal to exponent of minus delta E over kBT. And from this we can immediately find our temperature. So this temperature, okay, let's say 1 over kBT is 1 over delta E natural log of P ground over P excited. So if we flip this ratio here, that means we multiply the power of exponent here by minus 1, so we eliminate this minus. Then we take natural log, we have delta E over kBT, and then we get 1 over kBT as 1 over delta E to P ground over P excited. And then we can just insert values for P ground and P excited. And again get the same expression. Okay, here I have forgotten KB as usual. Well, mostly when doing statistical physics, typically this KB is assumed to be equal to 1. That means expressions that allows expressions to be simpler. Okay. The same result. Well, that means that actually negative temperatures are possible when we have a certain system whose energy spectrum is limited. But if we look at real-world systems, let's say we have some molecules, then typically not only molecule can be found in a ground or excited state, the molecule can move. So a molecule can undergo a translational motion. But translational motion has an energy spectrum which is not limited. Well, when V goes to very large values, to very high values, and approaches the speed of light, then of course for the energy we need to use the following formula for the kinetic energy. But the meaning is the same, that the energy of translational motion is unlimited. That's why typically you don't observe any negative temperature in real world, because mostly molecules and all of the systems which you study, they have this translational motion degree of freedom, which can allow them to attain infinite values of energy. And that's why this system is typically not being realized. However, you can realize negative temperature in an artificial system. When you design a system specially, so you can not achieve a negative temperature, but you can achieve quasi-negative temperature. Quasi-negative temperature. It means that, let's say you have a system which has translational motion degrees of freedom and also these discrete energy levels. And let's assume that thermalization, that as I have said previously on the first lectures in thermodynamics, we assume that for any system we have an equilibrium state. I have postulated it. We have an equilibrium state. But any system can be prepared in a state which is not equilibrium. And if we prepare a system in a non-equilibrium state, then after some time, which is called relaxation time, this system will get into an equilibrium state. And these relaxation times can be different for different degrees of freedom. So let's assume that for discrete energy levels in this system, the relaxation time, tau discrete, is much less than the relaxation time which equalizes a temperature between these discrete energy levels and temperature of translational degrees of freedom. Then for a certain amount of time, t, which is much less than tau translational, we can prepare a system in a so-called inversely populated state, this state is called inversely populated because the probability for population of the excited states is greater than the probability for population in the ground state. Inversely populated state. And for this small amount of time, this inversely populated state, we would have negative temperature in this discrete energy, in these discrete degrees of freedom, but we would have positive temperature in the translational degrees of freedom. But altogether, we can observe for a certain amount of time negative temperature in this system. Another way to create a system with a negative temperature is to maintain non-equilibrium state. This is what happens in lasers. When you have laser, you also have atoms in the ground and excited levels. And external pumping keeps your system in an inversely populated state. So that means that, conclusion of my talk today, that statistical physics allows you to determine entropy, and the entropy in a statistical mean is proportional to the logarithm of the number of states which realize your certain macroscopic state, which is called statistical weight. The entropy is proportional to the logarithm of the statistical weight, but also for systems with finite energy spectrum, we can attain negative values of temperature, and moreover, we can even realize these negative temperature states for a certain amount of time in a system which is allowed to evolve freely, or we can keep or maintain a non-equilibrium state with inversely populated energy levels. So that means that the system with negative temperature by supplying the energy from the external source. So when you are able to maintain non-equilibrium state, then you can keep negative temperature for a certain amount of time. So thank you for your attention, and I would like to finish the next lecture for today.